So usually it has this temperature probe. This is, I forget what they call that. It's a 3-letter acronym. It's not like a RTD. It's a resistance-based temperature. So the higher the temperature, the lower the resistance. Actually, I found out. Normally this goes on the coil, but it would now be outside on the inside, and it would be getting the air going into the coil, essentially getting your room temperature, and then that's what your thermostat and stuff on your original controls would be going with. I just unclipped them and moved it inside the door. And at first I had this inside too, thinking, oh, this will be inside temperature. Well, it doesn't work that way, because the logic of the controller is not meant for being a heat pump. It's only meant for air conditioning. So you need to fool it into going into air conditioning mode when you really are going into heat mode. So the way we did that is I found that 8,000 ohms of resistance on the input that this normally goes to, which is these white wires, will essentially, it's actually 2 resistors series together, these blue ones right here. If that is in your circuit, that is this just a big loop of the end of this. If that's in your circuit, it thinks it's 57 degrees. So then when you turn it on and you have it on normal cool mode, that just runs the fan. So then 91 degrees it's displaying right now, that was adding, this red resistor chain is a 6.7 k ohms, and it is going parallel to this other set. So it's not switching resistor values, it's taking this actually series 2 resistors and adding it in parallel to this series of 2 resistors. So it's a 5-volt DC reference that comes usually to the temperature probe. So it's coming in, it goes into a common contacts on this Honeywell thermostat, because this thermostat also has batteries in it, so it doesn't have to be 24-volt AC. It'll do all the switching, and essentially you just have dry contacts you can just do what you want with, as long as you don't overload them. So I'm feeding it the 5 volts directly from the air conditioner controls, the actual air conditioner controls, into here, and then the fan circuit goes through our 8K ohm resistor worth, and just goes into that Wago for, setup, testing purposes. Goes through the other white wire to it. It thinks it's 57 degrees, runs the fan because it thinks it's reached its target AC temperature. I have that set at like 75 degrees or so. So when it displays 57, it goes, oh, just keep running the fan. We don't need to run the compressor because we're already cool enough. And then the other part of that circuit, so it comes out of what would be your heat wire. So essentially kind of splitting that 5 volts coming in, right? We've got it coming in here is like it's common, and then it can go out through the fan, or it can go out through the heat. So when it comes out of the heat, there goes into our, well, it actually goes into the red resistor one, there's another wire there, and going through that, adding that 6.7 thousand ohms, goes into the input of this little Automation Direct timer. We're just using it as a timer only, and we're just set up just kind of a rudimentary defrost timer. So we're doing like 15 minutes run on right now for just testing purposes, and then once that, you see it's got 10.2 minutes left of its 15 minutes on, and then it'll go into a 3-minute, because it's not that cold out. The dew point outside is not outrageous like it was last night. Last night I was starting out just like 8 minutes on, 4 minutes off, and then I kind of made it like 8 minutes on and like 3.5 minutes off, and left it like that overnight, and it ran fine. Since we're just being a little conservative, since we're not doing like temperature-based defrost logic. So it comes out of the timer, and then goes in, then parallels here with our blue normal like fan resistor. So then when that parallel circuit gets added on, it actually lowers the total resistance value of the loop, and it lowers it from 8,000 ohms to about 3,200 ohms, I think, or so is how it come out. And then that value, that lower resistance value, makes it display 91 degrees. So then it goes, oh, we need to run AC now. Go ahead and kick it on. So then it runs it. So we've been running for a few minutes here. Coil temp on the inside-outside coil, the coil on the outside, 41.8 degrees, 34.3 degrees Celsius, the coil there, which, there's my chart. have a chart right here. There it is. So what are we at? 34.3 there we go. So 34.5 is 94 degrees. So we've got like 90, 93 and a half, something like that. We're almost 34.5. So it's almost 90. So it's essentially right at 94 degrees right now on the air, you know, the actual coil temp would be the air coming out. It's staying at 41.4 on the outside coil, so that's keeping it from, that should be high enough to keep it from immediately frosting up. If you get the coil temperature below like your dew point temperature, then it frosts up pretty quickly. So eventually I want to do, I've got a couple Arduinos and I want to do a more sophisticated defrost circuit so it can take and calculate the actual take the humidity and the temperature of outside and calculate a dew point, and then look at the temperatures of the coils and everything, and it can essentially have a smart defrost timer that it only runs the defrost when needed, and can if I give it enough information, it should be able to calculate its own COP and whatnot too. I could even give it like a current and voltage, I guess, input as well, and it could calculate its COP and its overall efficiencies, cost per running, all that good stuff. But it is working even on this just rudimentary setup right now fairly well. It got down, it was 36 last night. The dew point was like 34 or something, and it was keeping the shop up the temp. It wasn't really losing headway, or the workshop here. This is a 16 by 32 space. It's not huge. That's just an 8,000 BTU air conditioner. I think according to ChatGPT, it figured, based on the information I could give it, and it had to make a couple estimates because I wasn't giving it good delta T across the inside coil necessarily. I could give it a good delta T on the outside coil. I got two K-type thermocouples, the airflow going out the top, which would normally be your air conditioning out, and then like an air conditioner in, essentially outside coil in, outside coil out. But I only have, like out here, I don't have enough temperature monitoring to do it all at one time. So it had to do some estimating based on room temp and whatnot, and the values I gave it. But it came up with something in the, I don't know, 6,500, 6,700 BTU range is what we were essentially getting out of this system. And then on different timer settings, I gave it, it could calculate cost per run. And I think when I had it at 8 minutes on, 3.5 minutes off, it came up with something like $1.70 a day or so in a COP of like at least greater than 3. So this would be 3 times, 3 times the heat for the same electricity than straight electric heat, or you could look at it the same amount of heat for a third of the electricity usage or a third electricity cost. So, because the other way to kind of do stuff in the shop sometimes is that heater was really cheap to buy, but it's obviously very expensive to run. It's a 5,000 watt electric heater that, well, it'll keep up in here once you get it up to temp, but we're pulling like 600 watts while running here. Let's see if it settled down a little bit. Oops, I just fucking zeroed it. Gotta take it off and zero it out. Didn't mean to accidentally zero it. So it didn't settle down as much as I've seen it so far. But 5.2 amps at 115 volts according to that meter. Should plug it in good. This is also a Harbor Freight attachment, which actually works pretty slick for this purpose. I can't find my kilowatt meter. I forget where it's at. Otherwise, I'd plug that in. But anyway, I think if you do the math, you'll come out with something in the vicinity of 600 watts to make the kind of heat that we're making theoretically in the 6,500 BTU range or so, which would be, if that was electricity, straight electricity, I think is right now a different page, I guess. That's like 3,400 and change. So call it 3,500 BTUs per 1,000 watts. So we're getting essentially double that. We're getting like 2,000 watts worth for 600 watts, if that makes sense, because of the heat pump function, using the refrigerant as our. We're not taking electricity and making heat with it. We're taking electricity to manipulate refrigerant that is moving heat. So that's how we can get the coefficient of performance, or sometimes they'll advertise this. A heat pump is 300% more efficient than an electric heater. Like, well, that's kind of true, but you say it's got COP of 3, that doesn't mean anything to most people. But you say it makes 300% the same amount of heat, or makes the same heat at a third of the cost or something than straight resistance heat, then that makes more sense to people, I guess. So anyway, I'm going to keep checking this. It'll be interesting, especially when I set up the Arduino and we get some better data and more sophisticated defrost logic, and see what we come up with. So right there, it transition. Nope, it's still on. It's got 3.5 minutes left of it. It doesn't switch to go to its. It doesn't switch this 15 to like the 3 when you tell it to do it. And the reason I've set 3 as a minimum is because I know there is some sort of an offset on thermostat as well, but definitely if you stop commanding, like I just did there, stop commanding on the heat pump or the air conditioner. So see, it released, the timer opened the circuit, which released the red relay. I made it red for hot and blue for fancy. This is still calling for heat. This has interrupted that circuit, so only the blue resistor, the higher resistance, 8,000 ohms, is going through the loop. So that changed the temperature to 57. So now it thinks, oh, the guy has it set at 70. I have it set 70 degrees, and I've reached 57.